Okay, everybody, we're going to take a look at this now, and we're going to work on, we're back over here, the PDC project. We talked about this, and this is from over in chapter 13, where we were looking at decision-making under risk, and we were putting some probabilities to those risks and looking at some expected values based upon possible outcomes and our estimates of the probability of those occurring. And so we're going to take a look at this PDC model, okay? And it's just going to be, it's a little meticulous, and you just almost have to walk along. And here we have a data table. Now, before I do this, I'm going to make sure that we've copied. I think I've copied everything, and I'm going to insert a textbook. Okay, so I'll go over here and click insert a text, not a textbook, excuse me. I'm going to insert a text file, text box. Yee, here we go. Okay, and we'll put this into bold so we can see it. Okay. Okay. And so we're going to create a base case plus 3 scenarios. I'm going to do it like this. I'm going to click move or copy. Okay, I'm going to create a copy. Then I'll create another copy. And I'm going to create another copy. There we are. Now this first one that doesn't have a number in front of it, I'm going to rename this base case. Okay. Then this second one, I'm going to call it scenario 1. As you can see, we're going to create the tabs that will correspond to each of these 3 scenarios. Okay, so we've got the base case, and then we're going to have scenario 1, or name it. All right, and this other one, this one, next one here, we'll rename it scenario 2. And then finally we'll have this one we'll rename scenario 3. Okay. Now again, I think I covered most of chapter 13 sufficiently Monday. And if it's a little weak in your mind or maybe not stuck there, you'll want to go back and take a look at it. Of course, you have the textbook to take a look at as well. Okay, this is the PDC model. This is from chapter 13 of the Anderson files. Let's look at this and let's find out where in the world did we get this 7.7046. Well, it is the maximum of the following outcomes. Okay. And notice we have 3 scenarios. Pardon me. In the base case here, we're going to go over here to base case. Let's go base case where we need to be first. Here we go. And this is the outcome that we obtain. And notice we've got, it's the maximum of E6, E16, or E26, one of these 3 values. And so if we determine that we look at building a small medium, or large complex. And we've got these values. If we don't, they're either going to be 0 or this is what we'll get in terms of our return, pardon me, in terms of the return that we'll get using a small, medium, or choosing to build a small, medium, or large. Okay? And again, we'll look at these numbers. And this is going to equal A16. And the best decision is, and let's look at it. It says if, and this is the choose function. And we have an index number, that's B13. This is a little bit like, this choose is a little bit like the, like a lookup function, if you will. And I'm gonna have the index number, and that's B15. And the value 1 is small, value 2 is medium. And value 3 is large. And so how this works is we're going to choose the value based upon what's in B15. Okay? That's our criterion. And B15, as you'll notice, is this number 1, okay? And that's our choice. So if A16, which is this 7.7046, equals E61, and we have the E, we have this 1. We're going to get the maximum of these 3 again. Okay. And here we have lined up in the data table the probability that we'll have a strong demand, and then the expected value if we have a strong demand. So if we build a small complex and we have strong demand, then our expected value is the 7.7046. Okay? Now I'm going to click over here in this cell N, and we get equals A16. And of course, there's the 7.7046. Then we have to make a decision. What's the best decision to go with? Well, we're going to choose B15. Okay. And we'll pop this up here for a minute. And B15 is the index number, and that's 1. And then we have our alternatives, small, medium, or large. And that is what's the best decision to go with given this probability for a strong demand and the expected value. And our best bet here is to go with a small complex if we have a very, very low probability of strong demand. Okay? Now, Notice 7.7046 is our largest number. And that's the one we go with. Okay. Now, let's move along here for a minute and let's look at where in the world did we get this 0.995? Let's click on that. Okay, and this is 1 times, pardon me, 1 minus 1 times the exponent of A16 divided by 1. So we're going to take 1 minus 1 time the exponent of A16 over 1. And we'll look at that function, the exponent function. And it returns a raised to the power of a given number. Okay? So, look that out for a minute. And let's look at that for just a second. Now, this is going to equal A16 divided by 1. Okay? And we get the 7.7046. In other words, we get the figure itself divided by 1. Now let's look up here for a moment. And we're going to take 1 minus that. We're going to take 1 minus 1 times the exponent, and we get that figure, 0.995. And that gives us our probability for strong demand, the probability that we'll have strong demand, okay, and we'll build a small complex. Here we're looking at the probability that we'll build a medium complex if the demand is strong. And that's our payoff. Now, we use the ln function. Put this in here. Okay. And here we've done some they've transposed this So we have this, we have a conditional statement here in which we use it, put it into an absolute number. Okay. Now we come here and we're saying strong or weak. What will we get? And we work these through and we get the sum. Okay. Now, following this is a little bit tricky. As you can tell, I'm sitting here looking at it and kind of having to work my way through it. The textbook walks you through it. But what we're doing here is we're working with permutations, branching theory. We're using a decision tree. And so if we build a small complex, okay, this is what we get. Here's the probability that we'll build a small complex. We'll build a small complex with strong demand. Then we come down to the medium. We're using the exponent. And here again, the probability that if the demand is strong, we'll build a medium complex. This is our base case right here. Okay. And then it just simply branches itself off. Notice if we have strong demand, we would build 8. If we don't have strong demand, 7, and the probability of that. And that's literally 1 minus 1 times the exponent of that value. And we see just the best decisions given the expected value and the probability that the demand will be strong. You just have to kind of wind your way through this. It's a fantastic technique. That's why I said, we'll want to spend a session looking at this, because we're taking probabilities notice here 1 minus H1. So if we think it's strong, we'll build 8. If it's weak, we'll build 7. Yep, with 7. And the tree takes us through each of those permutations. Now, we're here in the base case, so let's leave it alone. So let's go over to scenario 1. Let's see what happens with some things. Okay. And we've got some issues here. All right. I was afraid of that. So let's just go back here for a moment. And we've got these, I forgot about doing, setting these values over. Got a table built in here. That's our problem. All right. All right. Let's go over here to scenario one. We've got all these. I don't want to take the time to recopy all these, so let's do this. Let's just come to the base case. This is going to be the simplest way to do it. Then we'll just take a look at what we've got. So my apologies about this. I forgot about the fact we've got these figures in here. We created that table there. We use the table function. I forgot all about that. Okay. Now, let's just go ahead and plug the data in and forget about the serials 1, 2, and 3 because we'll have to do a bunch of cell referencing and all of that, and I don't want to take the time or my time or yours to do that. So, in this base case, we know what we're dealing with, okay? So we're in scenario 1. Let's go up here to cell H1, okay? And we're going to change that from 80 to 70. And then we need to take a look at cell A16, look at the value. So I'm going to do this. I'm going to write in scenario 1. This is how I did it last time instead of all that crazy cell referencing. And my apologies, but okay, we're going to get here. Scenario 1, and we get a value of 7.5843. Okay? That's scenario 1. Now the base case, let's go back right here. I forgot about it. I didn't need to do all this. I'll go back and make that 80. And of course, our base case for outcome was 7.7046. Okay? So in scenario 1, and the probability of strong, this is going to be, in the base case, it's 80%. In scenario 1, it's 70%. Okay. We're assuming here that we have an 80% chance that the demand will be strong. We have a 20% chance that the demand will be weak. Now, when I change my estimated probability of whether or not it will be strong, then that correspondingly is going to change the percentage when it's weak. And so under scenario 1, we get 70% chance that we'll have strong demand, and then we'll have scenario 2. I do apologize I forgot about this last semester. I did make a note to myself to not mess around with making all those. So it's scenario 2, and in this case, in scenario 2, the demand will change it from 80 to 60%. Okay, and now we get 7.4769. Okay. And now we believe the probability that we'll have strong demand is 60%. And then finally in scenario 3, I remember when I did this last semester, where I missed myself was I spent 40 minutes in class using cell referencing to build those, and there's just really no reason to do that. Okay. Show under scenario 3, we change it from 80 to 55%. We'll go back to our base case for a moment. Now let's do the new, which is scenario 3, which is 55%. And now this time we get a 7.4272 outcome at 55%. So what we've done basically here in this tree table, well, we've used a table function here, that's for sure. But here's the gist of what we've done. We start off with a base case where we assume that there was an 80% probability that we'd have strong demand, and then we got the outcomes based upon the strong demand versus the weak demand, and the outcome that we got. We started out here with 80%, okay, and we're assuming that it's 80% strong, and so we get this value and we test it. Is this the best decision? And we use the choose function. And our index number is B15, and it's either small, medium, or large. Okay. Okay. Now, in scenario 1, we assume that the demand is 70%. And this time we get a 0.5843 result or outcome, where we assume that the probability of it being a strong demand is 70%. Okay. And a weak demand is 30%. And notice we see the expected value up here. And we choose the best decision, which in this case is to build small, because it still gives us the best outcome. Remember now, this is the maximum of those three. Then in scenario 2, okay, we assume that there's a 60% chance of strong demand. And now our maximum outcome, probably of the three possible outcomes, is this 7.4769. And that's our best decision, is to go small, because we get the best outcome. All right. And then finally, we'll go back to the 80 here. So we reset it kind of, and then we'll look at 55%. And there's our scenario 3. And there's our expected value. Okay? And I apologize about the putzing around with all this. So we're good here. I forgot about scenario 1, 2, and 3. We had to do some tricky cell referencing, and just no point in dealing with it when we can do it here and just record it. So I'm going to record this here. Okay. All borders. And there we have the outcomes. Now I want to show you the table. You remember, if you took the business problem analysis course, where we built a data table where we looked at different interest rates of the profitability index based on different rates of interest versus different annual incomes. Okay. Well, this is kind of the same thing because we're using the table function. Look what happens. Let's watch what happens. If we have 0% of a strong demand, okay? Then we get that 7.7046. And notice over here, if you watch the table, guess where it is? The probability of a strong demand. Now, this is just an outcome variable here, so don't get confused. I'm sorry I didn't point that out to you earlier. This just is a bin to throw this into. You come down here at 80%, you'll see, okay? And the best choice is decision is small, given an 80% probability of strong demand. If we assume there's a 70% probability, here we are. Okay. And I'll have to change this to 70%. And here we are. And then our best decision. And then if we assume there's a 60%, and if we look, here we are. This is a single variable table. We're looking at H1 table and then H1. Now, we went to 55%. There is no 55% on there, but notice we're at 7.4272. So we're right about in the middle here. But nonetheless, the recommendation is the best decision is to go small. Now, you say, well, when is it going to be anything but small? Let's take a look here. And we have the expected value, the probability of strong demand is 1. We did the table. And our best outcome is 20. And of course, we'll build a large complex. So I'm sorry about this over here. These making you create these is stupid. My problem, we could just put them in the data, put in the table. But notice what's happening with this value, okay? Because it is a value that's the maximum. The lower the probability of strong demand, the lower the expected outcome. We still build a small complex, but our expected outcome decreases. Conversely, the higher the expected outcome, i.e. the higher the probability that we're going to have strong demand, drives upwards this figure that we get, 7.7046, our expected value. Okay. Now the author's doing a couple of functions like the choose function, like the data, a single variable data table, things of that nature. But this is a nice little model that the authors provide us. Now, by creating the 3 additional tabs, I wasted some of your time and I apologize. Okay? But hopefully you'll watch this. And this gives us our choice. Only when demand is an absolute would our best outcome be to do anything except to build the small complex. Think of it like this. Let's say we have strong demand. If we build a small number of complexes, let's put this up here. Okay. Now this is the maximum of these 3 numbers. The expected value if we have 80%, if 80% of the market has strong demand and if only 20% has weak. It's a little counterintuitive, but think of it like this. If I have high demand, okay, and I build a small number of complexes, I'm going to have an advantage because I'll probably be able to get the maximum dollar for every single unit in that complex. If the demand is 80% strong, and we build a medium complex, we see the result we get. Now notice here, we're using the ln function. Okay. And just to remind us, we'll put equal ln. And that's going to give us the natural logarithm of that number. And notice it's the natural logarithm of 1 minus E7, which is this probability below, divided by 1 times 1. And there's, of course, the absolute value for the probability that it's going to be less, essentially, than 0, or really, really far out. And here we are. Okay. Well, I think you can see it's a tool that requires some thought. It's got some detail. It's an excellent tool to use. It walks you through the permutations of each of your decisions. And you can roll this into any one of a number of kinds of situations. You could look at the expected perfect value of information and so forth. I'm not going to do that. I think I did enough harm here with doing these silly scenario 1, 2, and 3s, which we really didn't need to do. Okay? But what we do find is this. In terms of the different scenarios, the lower the probability of a strong demand, the lower the outcome we get. But we choose the small complex. And that would also apply as we go down to 60%, then down to 55%. Okay, folks, I'd say that's pretty much it. It's pretty complicated. It's a bit to digest. I would encourage you to take a look at Chapter 13. It's just detail and just thinking about the permutations and how they work themselves out. And the author's using a choose function, a natural logarithm function, as well as a single table variable. And that's really about all there is to it. Good? All righty. I think I'll go ahead then and call it a day, and I'll post this for you guys so you have it in advance.